And now in this lecture we'll answer on two questions. In the first question, we'll find out the area of this circle that is inscribed by this trapezoid ABCD. And in the second question, we'll find out the length of this line segment QB that is equal to x. So we'll start with the first question. In the drawing, we have trapezoid ABCD that blocks this circle, or this circle is blocked by this circle is inscribed by this trapezoid ABCD. What is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. In addition, we know that this is line segment AM that is equal to A units in its length. This is line segment MB that is equal to B units in its length. Again, our mission is to find out the area of this circle. So, the first step, we will define the center of this circle. This point is point O. We will define the point of tendency of tangent AD with this circle. This point is point P. And we will define the point of tendency of tangent BC with this circle. This point is point Q. So here we can implement rule 2. So I will quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing, we have a circle. This is the common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, rule 2, they are equal to each other. That is to say, PA is equal to PB. So we can actually implement rule 2 in our drawing. In our drawing, if we focus on this common standpoint, point A, from this common standpoint, point A, we have two tangents to this circle, tangent AM and tangent AP. And according to this rule 2, they are equal to each other. That is to say, AM equals to AP. But AM equals to A units in its length, according to what is given in the question. Therefore, AP must be also equal to A units in its length. Likewise, if we focus on this common standpoint, point B, from this common standpoint, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B according to what is given in the question. Therefore, BQ must be also equal to B units in its length according to rule 2. So BQ equals to 2 units. Therefore, BQ must be also equal to B units in its length. So BQ equals to B units in its length according to rule 2. In the next step, we will join points O and P, O and Q together by straight line. Point O is the center of this circle. Point Q is the point of the circle itself. Therefore, OQ is the radius of this circle. So we will define the radius of this circle as x. So OQ equals to x. This is the radius of this circle. And because of the fact that the radius OQ is equal to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by a straight line. OP is of course the radius of this circle, that is equal to x. The radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we will do a construction. That is to say, from this point A, we will draw perpendicular on BC. Again, from point A, we will draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in BC. This point is point N. When doing this construction, we created here those two angles. Those two angles are defined as one-sided interangles and are located between the parallel lines AD and BC. Why AD is parallel to BC? Because of the fact that ABCD is a trapezoid. So those two one-sided interangles are located between the parallel lines AD and BC. And therefore, according to rule 17, the sum of those two one-sided interangles is equal to 180 degrees. So I repeat quickly on rule 17. According to rule 17, the sum of one-sided interangles between parallel lines is equal to 180 degrees. So in the drawing, we have line A that is parallel to line B, and line C, the red line C, intersects with those two parallel lines at those 2 points. And in addition, we have here those are angles alpha and beta that are defined as one-sided interangles. And because of the fact that those two one-sided interangles are located between the parallel lines A and B, the sum of those two one-sided interangles is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So we can actually implement rule 17 in our drawing. So as I already mentioned before, those two angles are defined as one-sided interangles and they are located between the parallel lines AD and BC. That is to say, AD is parallel to BC. And therefore, the sum of those two one-sided interangles must be equal to 180 degrees according to rule 17. So this angle equals to 90 degrees according to our construction. So 90 degrees plus the size of this missing angle in total must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction. This is to say, from this point O, we will draw perpendicular on AN. Again, from point O, we will draw perpendicular on AN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we created here the small polygonal AP OT. Inside this whole quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this four pieces again. In total, it must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this four pieces again must be equal to 90 degrees in its size. Likewise, inside this lower quadrilateral TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this four pieces again, in total it must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this four pieces again must be equal to 90 degrees in its size. So, the big angle POQ, in total, the size of the big angle POQ, in total it is equal to 90 degrees plus 90 degrees, that is 180 degrees. So I write it down. Angle POQ is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line segment POQ is a straight line. Line segment POQ is a straight line. And if line segment POQ is a straight line, then PQ is also a straight line. So line segment PQ is also a straight line. So actually, this shape APQN consists of four sides. 1, 2, 3, 4. So I write it down. Shape APQN consists of four sides. And therefore, this shape APQN is a quadrilateral. So write it down. Shape APQN is a quadrilateral. But we already found out that quadrilateral APQN has four right angles, and according to rule 5, any quadrilateral that has four right angles must be a rectangle if not a square. So we will write to this quadrilateral APQN as rectangle because it has four right angles. So I write it down. This is the big quadrilateral APQN. This is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side QN. But AP is 8, therefore QN must be also equal to a unit in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to x plus x, that is 2x, therefore AN, the opposite side AN, must be also equal to 2x units in its length. AN equals to 2x units in its length. What is the length of the missing 97 Bn? Bn equals to Bq minus Nq. So write it down. Bn equals to Bq minus Nq. So in total, Bn equals to Bq. Bq is B minus Nq. Nq is A. So in total, Bn equals to B minus A units in its length. Bn equals to B minus A units. So in the next step, I'll copy the right triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. AB, the hypotenuse AB equals to A plus B, Bn equals to B minus A, and An equals to 2x. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle A and B that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AN squared plus NB squared. So I'll write it down. AB squared, that is the square of the hypotenuse, is equal to AN squared plus BN squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 2x squared. 2x squared is 4x squared. Plus Bn squared. Bn is B minus A, therefore Bn squared is B minus A squared. So in total, we shall find out that A plus B squared equals to 4x squared plus B minus A squared. Here we will open the brackets on both sides of this equation, and we get that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times B times A. So here we have A squared on both sides of this equation, so A squared will get cancelled. We have also B squared on both sides of this equation, so B squared also will get cancelled. After we cancel those two expressions, on this side of the equation, we left only with 2AB. On the other side of the equation, we left with 4x squared minus 2AB. So in total, we should find out that AB equals to 4x squared minus 2AB. Here we add 2AB to this equation. And we get that 2AB plus 2AB is 4AB, so 4AB equals to 4x squared. Here we divide this equation by 4, and you get that 4AB over 4 is AB, and it is equal to 4x squared over 4 is x squared. So in total, you should find out that x squared equals to AB Our mission is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So total, the area of our circle must be equal to pi x squared. But we just right now found out that x squared equals to AB. Therefore, we substitute x squared here by AB, and we get that the area of this circle, that is the area that we are looking for in this question, is equal to pi times AB square units. And that is the answer to the question. And again, I actually found out that the area of this circle is equal to pi times AB square units. So we finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. Our mission in this second question is to find out the length of this line segment qubit is equal to x. We have to find out the value of x. So in the drawing, we have a semicircle. This is a semicircle. We know that AB equals to 30 units in its length. AB is the diameter of this semicircle. If the diameter AB equals to 30, the radius must be equal to half of it. That is to say, the radius of this semicircle must be equal to 30 over 2, that is 15. So, I write it down. The radius of this semicircle is equal to 15 units in its length. In addition, you know that this is called PA, or line segment PA, that is equal to 10 units in its length. Called QP also equals to 10 units in its length. And our mission is to find out the length of this chord QV that is equal to x. We have to find out the value of x. So in the first step, we define the center of this semicircle. This point is point O. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle that is equal to 15 units in its length. Likewise, OB is also the radius of this semicircle that is equal to 15. In the next step, we join points O and P together by a straight line. OP is of course the radius of this semicircle that is equal to 15. In the next step, we'll complete this semicircle to a circle. And we will extend the radius PO until it touches the circle. So actually, this is the touching point of the extended radius PO with this circle. So we will define this touching point as point M. OM is of course the radius of this semicircle that is equal to 15 units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle, vertex angles, is theta, then the size of this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. In the next step, we join points B and M together by a straight line. and prove that triangle APO can go into this triangle MOB. So why those two triangles can go into each other? First of all, side PO of this triangle AOP is equal to side OM of this triangle OMB. They are both the radii of the circle and therefore they are equal to each other. So PO equals to OM. Repeat again. Side PO of triangle AOP is equal to side OM of triangle MOB. They are both the radii of the circle that is equal to 15, therefore they are equal to each other. In addition, those two angles are vertex angles, and we know that vertex angles are equal to each other. So this is angle POA, or triangle POA, and it is equal to this angle, that's the angle MOB. Or triangle OMB. Repeat again. Angle POA in triangle AOP is equal to angle MOB in triangle MOB. They are both equal to theta, therefore they are equal to each other according to the rule that vertex angles are equal to each other. And finally, side AO of triangle AOP is equal to side OB of triangle OMB. They are both the radii of the circle and therefore they are equal to each other. So AO equals to OB. So repeat again. Side AO of triangle AOP is equal to side OB of triangle MOB. They are both and the radii of the circle that is equal to 15 units. Therefore they are equal to each other. So we actually proved that triangle AOP can go into this triangle OMB according to side angle side rule. That is to say, those two sides and the angle that included between those two sides in triangle AOP are correspondingly equal to those two sides and the angle that included between those two sides in triangle MOB. Therefore, those two triangles can go into each other according to side angle side rule. So I write it down. Triangle AOP congruent. This is the side of congruent to triangle MOB according to side angle side rule. Where those two sides and the angle that included between those two sides in triangle AOP that are correspondingly equal to those two sides and the angle that is included between those two sides in triangle MOB. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that side AP or triangle AOP is equal to side MB or triangle MOB. So AP equals to BM. So AP equals to BM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AP and MB, must be also equal to each other. But AP equals to 10 units in itself according to what is given in the question. So we can write that AC equals to 10 And for this equation, 10 equals to AP equals to BM, we will derive that BM is also equal to 10 units in its length. This is side BM, that is equal to 10 units in its length. This is chord PM. Chord PM passes through point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, PM is the diameter of this circle. So I'll copy this semicircle with the diameter PM, and we will analyze this semicircle. So actually, this is the semicircle with the diameter PM that I copied from the original drawing. Here, chord PM or line, chord PQ or line segment PQ is equal to chord MB or line segment MB. They are both equal to 10 units in their length, therefore they are equal to each other. So, in the next step, here point O is the center of the circle, and QB equals to X. This is the line segment that we are working for in this question. So in the next step, we will extend line segment PQ and line segment MB by a straight line until they touch each other, until they intersect with each other. This is their touching point. This is to say this is the touching point of the extended line segment PQ and line segment MB. So we will define this touching point or intersection point. This point is E, and we have actually the rule that states that if you extend two line segments that are equal to each other in their lengths, then the new extended line segments must be also equal to each other in their lengths. Therefore, according to the rules that I mentioned, we extended line segment PQ and line segment MB that are equal to each other in their lengths. And therefore, the new line segments, the extended line segment PE, must be equal to the extended line segment ME. So PE is equal to ME according to the rule that I mentioned. PE equals to ME. So here we have, this is triangle EPM. In triangle EPM, side EP equals to side EM. And therefore, this is an isosceles triangle. Side PM is the base of this isosceles triangle EPM. And those angles are defined as the base angles of this isosceles triangle. And you know that the base angles of any isosceles triangle are equal to each other. Anyway, I will prove in another prove why those two angles are equal to each other. According to the rule that in front of equal sides in the triangle there are equal angles. We know that EP equals to EM. So in front of this side EP we have this angle PME. In front of this side EM we have this angle, that is actually angle MPE. And because of the fact that those two angles are located in front of those two equal sides, therefore those two angles must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because of the fact that those two angles are located in front of those two equal sides, and therefore also must be equal to each other in their sizes. So in the next step, we complete this semicircle to a circle. So we have here, this is quadrilateral PQBM, and this quadrilateral PQBM is inscribed by this circle. And according to rule 16, if a quadrilateral is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. So I'll repeat quickly on rule 16. According to rule 16, if a quadrilateral is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. So in the drawing, we have quadrilateral ABCD that is inscribed by this circle, and because of the fact that quadrilateral ABCD is inscribed by this circle, the sum of its two opposite angles must be equal to 180 degrees. Those are the two opposite angles of this quadrilateral ABCD, and therefore the sum of those two opposite angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. Likewise, those are also the two opposite angles of this quadrilateral ABCD, and therefore the sum of those two opposite angles must be equal to 180 degrees. That is to say, angle 1 plus angle 2 is equal to 180 degrees according to this rule, rule 16. So we can actually implement rule 16 in our drawing. Why? Because in our drawing we have, this is quadrilateral QBMP that is inscribed by this circle, and therefore according to rule 16, the sum of which two opposite angles must be equal to 180 degrees. Those are the two opposite angles of this quadrilateral QBMP, and therefore the sum of those two opposite angles must be equal to 180 degrees according to rule 16. But this angle equals to beta, so angle beta plus the size of this angle in total they must be equal to 180 degrees according to rule 16. Therefore this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is actually the sum of those two opposite angles inside this quadrilateral PQBM that is inscribed by this circle according to rule 16. Likewise, those are the other two opposite angles of this quadrilateral QBMP. So the sum of those two opposite angles must be equal to 180 degrees according to rule 16. This is angle beta, this is the missing angle, so the sum of those two angles must be equal to 180 degrees according to rule 16. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the two opposite angles in sine quadrangle QB and P that is described by this circle. So we actually found out that this is angle beta and this angle is 180 degrees minus beta. Beta plus 180 degrees minus beta is 180 degrees. So the sum of those two one-sided interangles is equal to 180 degrees, and therefore whenever you have the sum of two one-sided interangles equal to 180 degrees, then they must be between parallel lines according to rule 18. Therefore QB is parallel to PM. QB is parallel to PM according to rule 18. So I think quickly on rule 18. According to rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between parallel lines. So in the drawing we have line A, this is line A, this is line B, this is line C that intersects with those two parallel lines at those 2 points. In addition, we have those two angles, alpha and beta, that are defined as one-sided interangles. And according to rule 18, if the sum of those two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. So if the sum of those two one-sided interangles is equal to 180 degrees, then line A is parallel to line B. Again, if the sum of those two one-sided interangles is equal to 180 degrees, so that is to say, if alpha plus beta is equal to 180 degrees, then line A must be parallel to line B. So actually, I've already implemented rule 18 in our drawing. Why? Because in our drawing we have the sum of those two one-sided interangles is equal to 180 degrees, because 180 degrees minus beta plus beta is 180 degrees, and therefore those two one-sided interangles must be between parallel lines. That is to say, QB is parallel to PM according to rule 18. Okay, so in the next step, I'll copy again this semicircle with the diameter PM, and we'll continue to analyze this semicircle. Repeat again that we found out that QB, line 7 QB is parallel to line 7 PM according to rule 18. Or chord QB is parallel to chord PM. Here OP equals to OM, they're both the radii of the semicircle or circle, and therefore they're equal to each other. The radius of the circle and the radius of the semicircle is 15 units in its length. especially this is the semicircle with the diameter PM that is copied from this drawing. QP equals to BM equals to 10 units, OM equals to OP, above the radar of the circle that is equals to 15, and QB equals to X, that is the line segment that we're looking for in this question. In the next step, we'll join points O and Q together by straight line. OQ is of course the radius of this semicircle that is equal to 15. Repeat again, we already found out that QB is parallel to PM according to rule 18. We join points O and B together by straight line. OB is of course the radius of this semicircle that is equal to 15 units in its length. Those two angles are defined as alternating angles and are located between the parallel lines QB and PM. Again, QB is parallel to PM according to rule 18. And because of the fact that those two alternating angles are located between the parallel lines QB and PM, they must be equal to each other according to rule 15. So, repeat quickly on rule 15. According to rule 15, alternating angles between parallel lines are equal to each other. In the drawing, we have line A that is parallel to line B. Line C, the red line C, intersects with those two parallel lines A and B at those 2 points. In addition, we have those two angles, alpha and beta, that are defined as alternating angles. And because of the fact that those two alternating angles, alpha and beta, are located between those two parallel lines A and B, they must be equal to each other. That is to say, alpha equals to beta. So whenever you have alternating angles that are located between parallel lines, then they must be equal to each other. You can implement rule 15 in our drawing because of the fact that those two alternating angles are located between the parallel lines QB and PM. QB is parallel to PM according to rule 18, and therefore those two alternating angles must be equal to each other according to rule 15. So if we define this alternating angle as alpha, then this alternating angle must be also equal to alpha according to rule 15. So in the next step, I'll copy this green triangle POQ and this white triangle QBO. And in your page, we will implement on both those two triangles the law of cosines, but before that, I will repeat quickly on the law of cosines. So what is the law of cosines? The law of cosines is true in any triangle. So this is triangle ABC, that could be any triangle. The length of side AB is A units, side AC equals to B units in its length. This is side BC, that is equals to C units in its length. This is angle theta. According to the law of cosines, the following equation is true, that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So, we will implement the law of cosines in this green triangle PQO. So, I'm copying this green triangle PQO, and in your page, we will implement on it the law of cosines. So really, this is the grand triangle PQO that is coming from the original, from this drawing. According to the law of cosines, in this triangle PQO, this is angle alpha, so according to the law of cosines, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. Then again, according to the law of cosines, in this triangle PQO, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. This is equation 1. In the next step, I'll copy this white triangle QOB here and implement on this white triangle the law of cosines. So really, this is triangle QOB that is coming from this drawing. According to the law of cosines, this triangle QOB, this is again alpha, so cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. This is equation 2. Repeat again, according to the law of cosines, in this triangle QOB, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have two different equations for cosine alpha. We have equation 1 and equation 2. Therefore, we return equation 3 that says that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. And again, equation 3 states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So cosine alpha according to equation 1 equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x squared plus 15 squared minus 15 squared divided by 2 times x times 15. Okay. So we focus on the denominator of those two sides of the equation 3. In both denominators we have 2 times 15, so 2 times 15 we get cancelled. After we cancel 2 times 15, in that side of the equation we left with 15 square minus 15 square is 0. So here we have left only with x square over x. X square over x is x. In the other side of this equation 3, we have 15 square plus 15 square minus 10 square divided by 15. So in total we found out that x equals to 15 square plus 15 square minus 10 square over 15. So x equals to 15 square is 225. So it is 225 plus 225, this is 450 minus 10 square. 10 square is 100, so it is minus 100 over 15. So in total we found out that x equals to 450 minus 100 over 15. So x equals to 450 minus 100 is 350 divided by 15. So x equals, here we divide both the numerator and the denominator of this number by 5, and we get that 350 over 5 is 70, and 15 over 5 is 3. So in total, we actually found out that the length of line 7 cubit that is equal to x, the length of line 7 cubit that is equal to x, it is equal to either 70 over 3 units in its length, or in terms of numbers, it is equal to 23 and 3 units in its length. Repeat again, I found out that the length of this 9/7 cubit that is equal to x, it is equal to either 70 over 3 units in its length, or in terms of numbers, the length of this 9/7 cubit that is equal to x is equal to 23 and 3 units in its length. So we finish with the second question. In the next step, I'll summarize the lecture. I'll start with the first question, of course. Our mission in the first question is to find out the area of this circle that is inscribed by this trapezoid ABCD. What is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. In addition, we know that this is line segment AM that is equal to A units in its length. This is line segment MB that is equal to B units in its length. Again, our mission is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And we define the point of tendency of tangent BC with this circle. This point is point Q. So here we can implement rule 2. Well, if you focus on this convex point point A, from this convex point point A, we have two tangents to this circle. Tangent AP and tangent AM. And according to rule 2, they are equal to each other. That is to say, AP equals to AM. But AM equals to A units in its length according to what is given as the question. Therefore, AP must be also equal to A units in its length according to rule 2. Likewise, if we focus on this convex point point B, from this convex point B, we have two tangents to this circle. Tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B units in its length according to what is given as the question. Therefore, BQ must be also equal to B unit in its length. In the next step, we join points O and Q together by straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. We define the radius of this circle as x, so OQ equals to x, and because of the fact that the radius OQ that is equal to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by straight line. OP is the radius of this circle that is equal to x, and because of the fact that the radius of P is drawn to point P, that is the point of tendency of tangent AD with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PQ. Tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we did the construction, that is to say from this point A, we draw perpendicular on BC. Again, from point A, we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC, this point is point N. By doing this construction, we can do those two one-sided interangles, and those two one-sided interangles are located between the parallel lines AD and BC. Why AD is parallel to BC? Because of the fact that ABCD is a trapezoid. So we have those two one-sided interangles that are located between the parallel lines AD and BC, and therefore the sum of those two one-sided interangles must be equal to 180 degrees according to rule 17. But this angle equals to 90 degrees according to our construction. So 90 degrees plus the size of this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the next step, we did another construction, that is to say, from this point O, we draw perpendicular on AN. Again, from point O, we draw perpendicular on AN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we can do quadrangle AP or T. Inside this quadrangle AP or T, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, inside this lower quadrangle TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So, the big angle, the size of this big angle POQ is 90 degrees plus 90 degrees, that is 180 degrees. Angle POQ equals to 180 degrees in its size. And you know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So P line segment POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. POQ is a straight line, PQ is also a straight line. And therefore, this shape APQN consists of 4 sides. 1, 2, 3, 4. Again, shape APQN consists of 4 sides. And therefore, shape APQN is a quadrangle. Shape APQN is a quadrangle, and we have already found out that in quadrangle APQN we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be a rectangle if not a square. So we refer to this quadrangle APQN as a rectangle because it has 4 right angles. Okay, quadrangle APQN is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle APQN, side AP must be equal to the opposite side NQ. But AP is there, therefore NQ must be also equal to AN in itself. Likewise, according to the symbol, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to x plus x, that is 2x. Therefore, the opposite side AN must be also equal to 2x units in itself. What is the length of this missing 97BN? BN equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So BN equals to BQ, that is B, minus NQ, that is A. So in total, BN equals to B minus A in itself. This is side AB, that is equals to A plus B. BN equals to B minus A, and AN equals to 2x. In the next step, by copying the right triangle A and B in an equation, we implemented the Pythagoras theorem on this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle A and B that are copied from the original drawing. So according to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AN squared plus NB squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 2x squared, that is 4x squared, plus BN squared. BN is B minus A, therefore BN squared is B minus A squared. So in total, we have found out that A plus B squared equals to 4x squared plus B minus A squared. We open the brackets on both sides of this equation, and finally found out that A plus B squared equals to A squared plus B squared, plus 2 times A times B, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared, plus 2 times B times A. So here we have A squared on both sides of this equation, so A squared will get cancelled, and we also have B squared on both sides of this equation, so B squared also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 2ab. In the other side of this equation we left with 4x squared minus 2ab. So in total we can find out that two ab equals to 4x squared minus 2ab. Here we added 2ab to this equation and found out that 2ab plus 2ab is 4ab, so 4ab equals to 4x squared. Here we divided this equation by 4. And finally found out that 4ab over 4 is ab, and it is equal to 4x squared over 4 is x squared. So in total, we found out that x squared equals to ab. Our mission is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of this circle must be equal to pi times the radius of this circle squared. So it is pi times the radius of this circle squared. The radius of this circle is x, therefore the radius square is x squared. So in total, we should find out that the area of this circle is equal to pi x squared. But we already found out that x squared equals to ab. Therefore, we substitute x squared here by ab. In total, we found out that the area of this circle is equal to pi ab square roots. Then again, the area of this circle is equal to pi times ab square roots. We finish with the first question. In the next step, I presented to you the second question, we solved the second question of this lecture. Our mission in this second question is to find out the length of this 97 cubic that is equal to x. We have to find out the value of x. So, in the original drawing we had this semicircle. AB equals to 30 units in itself. AB is the diameter of this semicircle. If the diameter is 30, the radius must be equal to half of it. That is to say, the radius is 15. So, in addition, we know that this is called P8. This is called P8. It is equal to 10 units in itself. This is called PQ. This is also equal to 10 units in itself. This is called QB, that is equal to x, and our mission is to find out the length of called QB that is equal to x. We have to find out the value of x. So first of all, we define the center of this circle. This point is point O. Point O is the center of the semicircle. Point A is the point on the semicircle itself. So for OA is the radius of this semicircle, that is 15. Likewise, OB is the radius of this semicircle, that is 15. We join points on P together by straight line. OP is also the radius of this semicircle, that is 15. In the next step, we completed this semicircle to a circle, and we extended radius PO by straight line until it touches the circle. We define the touching point of the extended radius PO with this circle. This point is point M. OM is of course the radius of this circle, this is 15. We join points A and B together by straight line. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. In the next step, we prove that this triangle PAO can go into this triangle OMB. So one of those two triangles can go into each other. First of all, side PO of triangle APO is equal to side OM of triangle OMB. They are both the radius of the circle, and therefore they are equal to each other. In addition, those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. And finally, side AO of triangle APO is equal to side OB of triangle OMB. They are both the radius of the circle, and therefore they are equal to each other. So, in total, we should prove that this triangle APO can go to this triangle OMB according to side angle side rule. That is to say, we prove that those two sides and the angle that is included between those two sides, this angle, the triangle APO, are correspondingly equal to those two sides and the angle that is included between those two sides, this angle, in triangle MOB. Therefore, we have proved that those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that side PA of triangle APO is equal to side VM of triangle OMB. And again, we derive that PA equals to MB. PA equals to MB according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say PA and MB, must be also equal to each other. But PA equals to 10 according to what is given as the equation. So we can write here that PA equals to 10, and from this equation 10 equals to AP equals to BM. We derive that BM is also equal to 10 units in its length. This is the side BM that is equal to 10 units in its length. PM, chord PM, passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, PM is the diameter of this circle. So in the next step, I copy this semicircle with the diameter PM and analyze this semicircle. So this is the semicircle with the diameter PM that I copied from this drawing, from the original drawing. Point O is the center of the semicircle. AM equals to OP, the above the radius of the circle, that is equals to 15. And PQ equals to MB, the above equal to 10 units in its length, and therefore they are equal to each other. QB equals to X, that is the line segment that we are looking for in this question. So PQ equals to MB. Those two line segments are equal to each other, they are both equal to 10, therefore they are equal to each other. In the next step, I extended those two line segments PQ and MB by straight line until they intersect with each other at this point E. And we have the rule that says that if you extend two line segments that are equal to each other in their lengths, then the extended line segments must be also equal to each other in their lengths. We extended PQ and MB that are equal to each other in their lengths, and therefore the extended line segments, that is to say PE and ME, must be also equal to each other in their lengths. That is to say PE is equal to ME according to the rule that I mentioned. PE equals to ME. So by doing this construction, we created triangle PEM. Triangle PEM, in triangle PEM, side PE is equal to side EM, and therefore this is an isosceles triangle. PM is the base of this isosceles triangle PEM, and those two angles are the base angles of this isosceles triangle, and you know that the base angles of an isosceles triangle are equal to each other. Anyway, I proved why those two angles are equal to each other. Those two angles are equal to each other according to the rule that says that in front of equal sides in the triangle there are equal angles. So in front of this side PE, we have this angle. In front of this side EM, we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta. Okay. In the next step, I completed this semicircle to a circle, and in the drawing we have quadrangle PQBM that is inscribed by this circle, and according to rule 16, any quadrangle that is inscribed by a circle, then the sum of its two opposite angles must be equal to 180 degrees. Those are the two opposite angles of quadrangle PQBM, and according to rule 16, the sum of those two opposite angles must be equal to 180 degrees. But this angle equals to beta, so angle beta plus the size of this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 16. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in quadrangle PQBM that is described by a circle, according to rule 16. Likewise, according to the same rule, the sum of those two opposite angles must be equal to 180 degrees. But this angle is beta. So angle beta plus this missing angle, in total, they must be equal to 180 degrees according to rule 16. Therefore, this missing angle must be equal to 180 degrees minus beta. Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in quadrangle PQBM that is inscribed by this circle according to rule 16. So if we found out that this is angle beta and this angle is 180 degrees minus beta. But 180 degrees minus beta plus beta is 180 degrees. So we have here two one-sided interangles, and the sum of those two one-sided interangles is equal to 180 degrees. And therefore, according to rule 18, whenever we have the sum of two one-sided interangles that is equal to 180 degrees, then they must be between parallel lines. And therefore, those two one-sided interangles, that the sum of them is equal to 180 degrees, must be between parallel lines. That is to say, QB is parallel to PM according to rule 18. QB is parallel to PM according to rule 18. In the next step, I copy this semicircle with the diameter PM, and we continue to analyze this semicircle. So actually, this is the semicircle with the diameter PM that is copied from the original drawing, from this drawing. Here, OP equals to OM equals to OQ equals to OB, above the radius of the semicircle, that's equals to 15. QP equals to MB equals to 10, and we have already found out that QB is parallel to PM according to rule 18. Again, QB is parallel to PM according to rule 18. So those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM, and therefore they must be equal to each other according to rule 15. Rule 15 states that alternating angles between parallel lines are equal to each other. So those two alternating angles that are located between the parallel lines QB and PM must be equal to each other. So if this is angle alpha, then this angle must be also equal to alpha because they are equal to each other according to rule 15. So in the next step, I presented to you the law of cosines, and we implemented the law of cosines in this right triangle PQO, and in this right triangle QOB. So what is the law of cosines? The law of cosines is true in any triangle. So this is triangle ABC that could be any triangle. AB is A, AC is B, and BC equals to 3 units in its name. This is angle theta. In this triangle ABC that could be any triangle, the following equation is true. That cosine theta equals to A square plus B square minus C square over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square over 2 times A times B. So in the next step, I copied this right triangle PQO in the new page, and implemented the law of cosines in this green triangle PQO. This is the green triangle PQO that I call it from the this drawing. So according to the law of cosines in this triangle PQO, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. Again, according to the law of cosines in this triangle PQO, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, I copy this right triangle QOB here and implemented the law of cosines in this right triangle, triangle QOB. According to the law of cosines in this right triangle QOB, cosine alpha equals to x square plus 15 square minus 15 square over 2 times x times 15. Again, cosine alpha equals to x square plus 15 square minus 15 square over 2 times x times 15. So we have two equations for cosine alpha, equation 1 and equation 2. Therefore, we created equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Again, according to equation 3, cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 1 equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x square plus 15 square minus 15 square over 2 times x times 15. In the next step, we focus on the denominator of those two expressions. We have on both denominators 2 times 15, so 2 times 15 will get cancelled. After we cancel 2 times 15, in this side of the equation we left with 15 square minus 15 square, that is 0. So we have here only x square over x, that is x, so we left only with x in this side of the equation. While in this side of the equation we left with 15 square plus 15 square minus 10 square over 15. So in total we actually found out that x equals to 15 square plus 15 square minus 10 square over 15. So x equals to 15 square is 225. So we have 225 plus 225, that is 450, minus 10 square. 10 square is 100, so it is minus 100 over 15. 450 minus 100 is 350. So in total this expression equals to 350 over 15. So x equals to 350 over 15. So here we divided both the numerator and the denominator of this number by 5. We found out that 350 over 5 is 70 and 15 over 5 is 3. So in total we found out that QB that is equal to x, it is equal to either 70 over 3 units in its length. In terms of numbers, QB is equal to x, it is equal to 23 and 3 units in its length. I repeat again, once we found out that the length of this line segment QB that is equal to x, it is equal to either 70 over 3 units in its length. In terms of numbers, the length of this line segment QB that is equal to x, it is equal to 23 and 3 units in its length. Okay, thank you very much.